Welcome to the lesson video on the maximum margin classifier. We're going to start this video by walking through a toy example that's going to motivate our ideas with the maximum margin classifier. And so here I have a data set with two classes I've just made up. Suppose I'm going to try to use something that estimates my classification assuming some distributions for the data. And suppose let's pick QDA. So I estimate the mean for my red data is about here. And then if I model this with a probability distribution, it probably would look something like that if I assume it has a Gaussian distribution. And then for my other data, maybe it has distributions that look like this. And so my separation maybe comes in somewhere there. Right, for quadratic discriminant analysis. So we're assuming different Gaussians for these data. Now there's a lot of different things that we could talk about that might be problems with this. Certainly if things are estimated the way I have, you have an error, a misclassification there, but it just doesn't seem to be the right way to model this data. Right, if we just look at this data by itself, it's pretty clear there's a linear separation. I can pretty much do that and say that would do a pretty good job. The question is, how did I see that? Right, I didn't model these distributions as some sort of distributions for these two classes. I just looked at it and said there's a gap between them and I can fill it with a line. Now, how did I know to pick that line and not this line? Both of those lines that I just drew would be perfect classification results. And so any sort of cross-validation isn't going to pick between these. So why? Visually, clearly that one's better, but why? How do we know it's better? And if you're looking at and trying to figure out the why, this data point and that data point are close to this vertical line that we would say is perfect but bad. This line that we're going over, it would give perfect results. Everything to the left is blue, everything to the right is red, but it's close to two of the data points. That seems to be not something that's robust, because if there's a little bit of error in one of these data points, it would be easy for it to jump to the other side of the classification line. So what we're going to talk about with the maximum margin classifier is this. We're going to look for a separating linear plane, or in this case it's just a line, but a linear subspace that's going to separate our two classes, where the distance to all the nearest data points is as maximum as possible, as large as possible. That distance to those closest data points is called the margin. Think of it as like a margin for error. With some error in those data points or some noise, and they moved around by some amount, that margin tells you how much error there could be without crossing the separation curve. And so that's the motivation behind the maximum margin classifier that we're going to talk about today. Now, it turns out it's really a fundamental building block for more complex classifiers that are more sophisticated and more robust, but it's of interest on its own, and so we're going to talk about it on its own today, and then in later lessons we'll use it to build something called the support vector machines, which is superior to a lot of other algorithms, which by far are one of the best performing algorithms in a lot of types of data. Okay, so the maximum margin classifier, what is it? It's a classifier where we find the linear separation surface or hyperplane or plane that has the maximum margin. Remember, the margin is the distance to the closest data points. Why would we do this? Why would we use this as a classifier? The maximum margin separation is based off points in the classes near the margin. And so this, in a sense, it optimizes by the things you need to separate. Those are philosophically, for the maximum margin classifier, the most important points, right? The ones that are near the border between the classes. So we're looking for separation based on those most important points. What does this do? This creates separation for non-Gaussian classes, right? LDA and QDA are really good when you have Gaussian classes, but if they're not Gaussian, those methods aren't going to work very well, or might not work very well. And so maximum margin classifier works well for non-Gaussian classes. And using this maximum margin gets a separation that should be robust, right? We talked about if some of those points have a little bit of error in them, they're not going to jump across the separation plane unless that error is at least as large as the margin. Okay, so let's talk about some definitions. Let's be a little more formal than our early pictures. First thing we want to define is the separating hyperplane. And so the separating hyperplane is an p minus 1 dimensional plane, where p is your number of feature variables. And it's given by this formula shown here, this formula here. And we have a linear function of the x's equal to 0. And that linear function of x's is why we sometimes call this a linear separation. And it's what defines in 2D a line, or in n dimensions an n minus 1 dimensional hyperplane. Or sometimes we just call it a plane. Often when things are greater than 3 dimensions, it's called a hyperplane, but it could also be called a plane. Now, with the meaning of these betas, if we're in whatever dimensions that we're in, if you take the betas greater than 0 and you make them a vector right here, that vector will give you the normal vector to a plane. And so this shown in this picture in blue would be our separating hyperplane for this set of betas. And if we're in 3 dimensions, you'd need, of course, 3 betas here. Beta 1, beta 2, beta 3. What does it mean to be normal? That means if you look at this vector, it's perpendicular to the plane in any direction, or forms a 90-degree angle to the plane in all directions around the plane. So next thing we need to define is the margin. We've talked about this. This is the distance from the separating hyperplane to the points that in each of the classes that are closest to that separating hyperplane. The points that are on the these dashed lines that are a distance away from the separating hyperplane equal to the margin, these points are called the support vectors, right? They are the points that give support to our separating hyperplane. The way we implement this in software, well, it's not a central focus of this course, but we want to talk about it. It's implemented as an optimization problem. And so the way this problem works is by the following, this sort of prescription that we have on the page here that describes this optimization problem. So this first part says that we want to find the betas in resulting margin M, or associated margin M, that would result in the maximum value for M. Remember, M is the margin. Subject to this formula here. And remember, we talked about the beta j's, where j goes from 0 out to p, right? All the betas after beta 0, they're the normal vector to the hyperplane. And so this formula here says we want that normal vector to have length 1. What that does is it makes formulas work nicely, but it also forms a unique solution. So it's more of something that makes things tidy as opposed to something that's essential for the classification. And this third line in the optimization says that the classification must be correct with distance to the separation curve, the separation hyperplane at least M. And so this part in this formula is the set of feature variables for an observation, for observation I, evaluated at the formula for the hyperplane. And then we multiply that by yi, which in this case is 1 if you're in class 1, and -1 if you're in class -1. And this formula here, because of that normal vector, gives the distance to the hyperplane. And so we want the distance to the hyperplane, and it's a sign distance. One side, it's the distance, and the other side is negative the distance to the hyperplane. And if it's negative distance to the hyperplane, that's the side where yi would be negative. And you'd multiply the two together and get a positive number, and then the distance has to be greater than or equal to m, which is the requirement over here. So this whole formula just guarantees that we're getting correct classification, and all of our distances to the hyperplane is at least capital M. So this defines capital M as the margin. Now this is all implemented in software. In this course, we're not particularly concerned with how it's implemented, but this is the prescription for that implementation. So there's one drawback for the maximum margin classifier, and it's kind of an enormous drawback. It only works when you have a linear separation. And so it doesn't become a very generally used classifier on its own, but it's a building block, as we've said, for more complex and more robust nonlinear classifiers. Okay, so what we talked about in this video today, we talked about the maximum margin classifier. It's a classifier where you find the linear separation surface with the maximum margin. And the margin is the distance to the closest points in each class. Why would we do this? The maximum margin separation is based off the points in the class near the margin. So there's some good motivation for this separates using the points that matter most, the points that are the ones that are likely to be unclassified or classified improperly. This enables separation for non-Gaussian classes, right? If my data classes were each Gaussian distributions, I would just use LDA, right? That's going to give you something that's very close to the Bayes optimal separation surface, and it's hard to beat for things that are Gaussian. But for non-Gaussian, maximum margin classifier provides potential benefit. Maximum margin classifier gets a separation, should be robust, right? Talking about when you can find that separation. It gets the maximum, or if you think of the margin, it's the amount of error that could occur, or noise, or change in the data points close to the separation plane. And if their noise or change in values is less than the margin, then they remain classified properly. But this is the big but that makes maximum margin classifier not generally useful. This only works when classes are linearly separable. So if you have one data point over on the other side, for whatever reason, you can't solve that optimization problem. So this is really, maximum margin classifier is a building block for more robust classifiers. Thank you very much.